Hello, everyone. It's really an honor for me to be here to present some of my work on machine learning applied to performance optimization, social and effective computing. So in my talk, I will go over, I'll try to answer 3 questions, the 3 W's of the machine learning. Why now? Why everyone is really on this track? Why machine learning? What is machine learning? If you want to describe it in non-engineering and dilute all the math and the algorithms from that term, what would machine learning be? And then the last W that I would like to present to you is the where, and more specifically, where in our lab we have used machine learning. So why now is the era of machine learning? I think it's because we have the trinity of big data. You've heard so much about it all today and probably in the remaining sessions as well. So we have the data, we have the hardware, and we have the algorithms. So a lady had asked before, if you want to be in the machine learning, you could be at the algorithms level, but at the same time, to really be able to produce meaningful algorithms along the line of deep learning, swarm, heuristics, bio-inspired, statistical, you name it, you have to have data. And the data has to be well acquired, and this is why the hardware, and it's spanning from the IoT, the cheapy wearables that we have, the smartphones, the data centers, and now the fog computing. So if you want to be in any of these categories, eventually you're working indirectly in the machine learning. We need to be able to have the hardware to sense, or the algorithms, the code to be able to synthesize and understand the information from the web. We need to be able to run it efficiently on hardware, and we need to run it according to the algorithm so that it makes sense. So with this trinity together, we could say machine learning is what? Basically, machine learning, if I want to abstract it from the math, is I have data, and then I'm after this function that will make sense from the input that I have to the output that I would like to get. So what is Y going to be learning? How do we prepare X, the input that I have? Is it noisy? Where is it coming from? Is it coming from different sources? Do I have to maintain some sort of scalability? What should F look like? Would it be very nonlinear, linear? What type of function would be able to explain my X to my Y? How do I evaluate my F? I spent so much time in my lab developing this function, but then how good is it? How can I really find the boundaries, its performance? And then mostly the $1 million question is really, what is F? What could be the best function for really most of the applications that we touch base on that would really be able to explain everything that we sense we have as a data with respect to the outcome. So with that, I get you to the what, the where. So where's the machine learning applied? This morning and the morning sessions and this afternoon session, we've talked about so many of the machine learning applications, and I'm sure there's tons and tons out there. I've had in my book some other examples, but I picked just the 3 to discuss today with you. It fits probably more the traditional, the engineering background, which is power reduction in adaptive processors. And then I picked 2 other applications that are probably more the artistic or maybe the non-engineer, so that we're not coined with the very traditional people. So power reduction in adaptive processors. Why is that? So now it seems like we live in a very nice era. It's digital. We don't have to worry about writing, printing, mails, all that, all jargon is away. We're talking about connectivity. We're talking about devices that are very smart, IoTs. Maybe the coolers that Professor Ghaddar was mentioning, they will be controlling our life, our smart living. Everything will be so seemingly and nicely operating, and we're just enjoying that. But this really comes, this digital technology era is coming at an expense of much more stress and much more strain on the data centers. And now we talk about farms of data centers and huge computing systems that should really be analyzing all this trend, all this big data, storing it and making sense out of it, which means it is really consuming more power. And with that, some people even went to say, maybe computing is the next new pollutant. If we are from an environmental perspective looking at things, irrespective of, we're not talking about the production needs from an electricity perspective to build all these equipments. We're just talking about the runtime and their consumption. In this slide, there are two figures showing the total regional data center power consumption for the EMEA. And you could see these numbers are pretty significant. And this lower table is for the US, showing how much we need in terms of energy, how much we need in terms of power plants, just to make sure we are providing enough of power for our data centers. So why do we want to worry about that? It's because most of the data centers, they do run on generic or standard. They're not, at least for most of the time, they're standard computing platforms, which means that the designer who really built this hardware, this server, and these farms of server, they have designed it in mind to be, on average, good for most of the applications. So if we are doing Skype, we will be exercising different needs from the hardware. If we're doing a YouTube download, we're chatting, we're running simulation on the cloud. So every type of application would require different needs from the hardware. But the hardware that is running in the data centers has been configured, most of its parameters, let's say the branch predictor, the ALUs, and the caches, the memory sizes, all of this has been developed so that it is good on average. So what would be nice, and this is what we have done in this project in collaboration with Intel, we tried to look at what would it take, or how much would I really improve if I were to dynamically change the configuration of my processor when my workload is running. So with that, we were able to see, to use one of the very famous machine learning algorithms, support vector machine for regression. We have adapted it to make sure that we do not underestimate, because this is a major problem. If I do not give enough of power for my microprocessor or my server, the job will become stalled, or it will throttle or something. So I wanted to make sure I can predict, and I want to penalize, I want to avoid the under prediction, because this is not what I want. So we modified this algorithm. We were able to run it on a couple of benchmarks, and we were able to reach a 17.8 decrease in power, which was very interesting. And this resulted in a couple of publications as listed on the slide. So that was my strict engineering, very square example about machine learning and power and optimization and environment and saving the planet. And now I move to something more fun, which is the Arabic bubble speech. Do you know what the bubble speech is? It's another word to refer to the comics. And what we wanted to do here is like, why comics? And probably why Arabic comics? So Arabic comics are around, and we might not be aware, but it has been around for like a century or so. It really expresses our cultural heritage, and it's a way of expressing the culture. Maybe this region has been through a lot of different ideologies, and it's very well captured in these comics. It has diverse content, and it's most of the time very inspiring for children, and I would say even for adults. So what was our research question here when we were looking at this data, at this information? So we had the visual content and the actual text inside this bubble that we analyzed. So we had to run and do some natural language processing to extract the words from the bubble. So we had to write and code something to automatically extract the bubbles, identify the text, do the pre-processing on the text, understand the context, and then map it back to the colors and to the tone and the comics. And we wanted to see if the content from a language perspective was appropriate. And the second question, we wanted to see if the visual was in accordance to the text that was inside. And we found a lot of interesting relationship. So we used the machine learning and the natural language processing, support vector machine also for that. And at the end, we ended up finding a couple of comics traced back to the author, having some, I would say, intentional maybe misdirection and some emotional illusion throughout the optical representation, and this is not matching the semantic messages. Also, this work has been published in a couple of conferences and journals. Another, maybe, a different application for machine learning we worked on is to try to see if we can leverage the media, and more specifically Twitter, to help in managing crisis better. And why Twitter, or why maybe the social media, I would say first, is because we have a lot of information out on the web, and many times the current situation in the relief aid is to go through reports, phone calls, send people on the ground, and so on and so forth. And if you look at the numbers for the natural disaster statistics, they're quite significant. So what we tried to do is we developed a framework to collect a lot of data from the web, images, and map it back to the tweets that goes with it, and understand the context of the text together with the content of the image, and try to see if we can really say that an annotated image is better than just sounded of word. That's like updating the folk statement. And it was very interesting that we were able to describe up to 92.43% using some biologically inspired machine learning algorithm that we also had to modify. So we were able to differentiate between a natural disaster hitting in an urban versus a non-urban environment. And finally, my last slide is about affective computing. So also, we want machine learning to do, all of this maybe skilled or technical challenges for us. But we wanted to see, can machine learning, let's say, move more into something that is somehow more subjective? Maybe recognize the style of a composer, and we're talking about classical composers, just based on, a fragment of their composition. So the style, try to get the era in which this was written. So this is what we tried to do. And try to see if from EEG I can also extract the emotion. And this is what we have done, also based on some biologically inspired computing that we also have to modify to make sure that we're capturing the peculiarity of the data. And we reached interesting results that also were submitted for publication. And with that, I finish my presentation.